Okay, so let me go to the next example, but before I will say something about the protonation state. So, for instance, here with the one QRA molecule that we have been looking at, you can go to structure and manipulation, and then go to a prot state. And then if you click upon some residue that can be protonated, then you can choose the type of protonation, right? So if it is one of the established protonation states, then, and your residue doesn't need to be modified, then you can choose these options. Another feature that we haven't explored is the mutation, right? And it's quite good because this makes the process of mutating proteins very easy to do. So I remember that before we had this type of tools, we have to do the text editing on the configuration files, and that was cumbersome somehow, right? But now the field has evolved a lot, and we have at hand different tools like this QuickMD. So now I will give you a touch of how the text editing looks like. So for some specific cases, it could be the case that you cannot do the pre-processing with QuickMD, and you need to do that manually, right? But in most of the cases, I would say QuickMD is just enough. We have seen how the protonation states can be done, right, by using QuickMD. But now let me move on, and we will try a setup with the command line. So if you're sitting here in the MD Orca example, sorry, no, it's not this one. I will move to the instructions for the Gaussian case, which is MD, QMM, QM, and NAMD. And in this case, in the case of NAMD Gaussian, we have the following instructions. So I will move to that folder in my repository. The folder that we are using now is the MD QMM NAMD Gaussian. And the instructions are here displayed on this side. So I will start with loading the modules. I will purge first. And this is a good practice, as I said before. There is no reason really why I need to change the VMD version. But at the moment, when I wrote these instructions, this version was available, and that's why I used that. But for the QMM simulations, the latest version that is installed on VMD is more suitable because it has the QMM part. So let me start VMD. And here, I will go to File, new molecule, and browse and choose the 4ake.pdb. And this is directly the file that I got from the protein data bank, right? I haven't modified that. And as you can see here, the instructions or the information is from the PDB data bank. So then load the structure and close this window here. So here you can see how the structure looks like. So it has some chains, right? It's not just one protein chain, but there are several chains, I remember. So now we can go to extensions and the TK console. And then here, if you are not working on this folder that is sitting in QuickMD, then you will need to put or type this CD and the path to the PDB file, because the TK console will not recognize that you are working on this particular folder, right? So, but in this case, it will recognize that. So I will start with these instructions. I will set now some variable called chain A, and I will select some atoms. And in particular, I will select just the chain A, right? But it depends on what you want to do. Also in the crystal structures, sometimes one chain has a better resolution than the other. And then you can choose the one that you want, right? That fits best to your needs. Then I will type chain A, $chain A. The dollar is part of the command, right? So you need to type that, write PDB 4ake, and I will give it some name like underscore chain A.pdb. And this will write the chain A only, right? And finally, I will quit VMD. If we check now our folder, you will see that you got this new chain A file here. Open your preferred text editor. So I am biased towards VIM, but you can also use Nano or Emacs or whatever you want that is installed in your local resource or here in QuickMD. I will use VIM and open the file. So in VIM, I can locate the atom number by typing slash, which it means search, and then the number of the atom, and this will put me directly into the atom that I want to delete. So if you take a look at the structure, you will see that these two atoms are the same, and I will prefer to use that because it's more suited for me, but it depends also on the chemistry that you want to study. So this is an extra atom. I don't want that for the present case. Delete it. And then now I have my chain. Okay. So for the present case, I will use the charm 36 set of parameters, right? So the way to proceed in general is by going to the website of the force field website. And here you can see all the force fields that are developed by this group. They have done a great contribution by setting up the parameters and the topologies for the molecules. And this was initially developed for the charm software, but it has migrated to other software. And in particular, you can get the equivalent to the GROMACS format also on this page. And at the moment that I wrote this file, these scripts, this version was the latest one to the July 20. That's why I'm using that, but you can also use other versions. So the way to proceed is to download the parameters. And I thought that this could be a kind of slow step in somehow depending on how you were working or how we will deal with the course. So I already did this step and I put already the files that are relevant for this case in this folder, right? So, but in general, you need to download the parameters and put it in your local folder. So the parameters relevant for this case are the topology for the proteins and also for the waters and the parameters, yes? So these are the files that we will use. And maybe some basic words or brief words about the topologies. For instance, if you go to the topology file that I mentioned previously when we talk about the protonation states. So you can see, for instance, how arginine topology is set in charm force field. So you can see how the molecule is arranged and the groups. These are the partial charges that are used for the arginine. And these are the atom types that are set in the parameter files, right? These are some extra information. And if there are some protonated states, then there should be present as well. For instance, let me see if there is something for ASP. So there is an ASP for the unprotonated state. No, for the protonated state, sorry. And there is also an ASP for the deprotonated state. Right? So if you need to modify this file, then you can follow the syntax and also the recommendations on this website, right? They have done the optimization and parameterization of the charm force field. Okay. So now we need to work more on this setup. So I will create a file called forake.pgn, no, pgn, and it will contain the following instructions. I will just copy and paste. This will call the PFGen plugin from VMD to generate the PSF file required in NAMD. And this will read the topology file. In the crystal structure, there are some names for the atoms, but in the parameter and topology files, there are some other names. And that's why we need to change the name of the residues. And also some atom names that need to be changed. Here, we will read the chain that we have written before. And the coordinates. We are guessing some coordinates for the atoms. And here we write the coordinates and we write the PSF file. So this is how a PSF script looks like. This will generate the coordinates together with the hydrogens for the protein chain, right? And also the PSF file, which is required in the simulations. Then we can use the VMD in the text mode to generate all these files. And just exit that, type exit and enter. So if you check again, you will see that the two new files with the coordinates and the PSF appear. You can visualize these files at this point, right? If you type VMD and the name of the file, .pdb, you will see how it looks. You can see the missing hydrogens and yes, and this is the initial structure. So I'm being very direct with the instructions that I said for the missing hydrogens, for instance. But in some cases you need a specific hydrogen location. For instance, if you are starting with a proton transfer reaction, in that case, you need to set the hydrogen's positions according to some other software or according to some manual setting, for instance. But in this case, I'm being just direct with the setup and doing the rough setup, so to speak. So let me go again on VMD, and then I will use the TK console. And here I will solvate the system by using the solvate package. Then solvate for AKE core.psf. And here I'm calling the generated PSF file and also the PDB file. Now I will set a box which has a margin of 10 angstrom from the longest position in the protein. And finally, this will output a file called 4AKE underscore WB. So, okay. So we can go onto the ionization. And for that, we will use the generated files. So we will call the auto ionize plugin. The PSF file is the one that we have generated, called underscore wb.psf. And the PDB file is the corresponding PDB. Yes. The solid concentration is 0.15. And the cation is sodium. You can also choose another cation, and this will set automatically an ion. In this case, it will sodium chloride. Okay, so now I will quit VMD. So if you check the files that were generated, we see that now there is an ionized and file, right? So just for convenience, I will modify the names and I will call ionized.pdb to something like 4AKE ion and PDB. And do the same for the PSF file. Now on VMD, I can open the ionized and solvated file, right? So it will look like this. I can choose, for instance, only the protein or the protein or ions, and this will show me the ions that are present, right? Okay, now let me open this file. The same, I shouldn't close it, but I didn't pay attention to my instructions. Then go to the TK console here. And this is important. We will get some statistics, initial statistic for this system. So we collect the statistics of the cell, so to speak. We select here all the atoms. And then measure the minimum distance, minimum and maximum distances in this system. And also measure the center, where the center of the cell is located. Now, very important, we need to save this information, especially the center of mass. So I will just copy these lines, and in some other file, I will open now a tab in my terminal, right? Which will put me in the same directory where I am working now. And I will create here a file called, for instance, statistics.txt, and you can call it with a name you desire. And here I'm using the initial information for the maximum and minimum distances, and also for the center of mass of the system. And we will need that later on. That's why I said here we need to keep a record. Okay, so quit VMD. And now, just to give you a feeling of how working with the text editor and the files look like. So we will try to modify the files that I provided to you. In particular, we need to go to top part and water and ions. And if you look at this file that was downloaded from the Makerel's website, you will see some values and options that are not recognized by NAMD, right? In particular, in Charm, these things here are environment variables that are passed to the program, and in general, they are not recognized by NAMD, and we need to deal with this stuff. And also, there are some options for the atom types and parameters that are not recognized. And of course, you need to add new parameters. You need to modify these files. So here I said that we need to comment out the lines 36 to 30, 35 to 36, the line 40. Now I will move to the line 319 and 320. I need to comment out the line 22, the 24 to 27. And these are options for the Charm package, if you are familiar with that. And go to 346. This is one atom that will not be used today, and it's not recognized by the parameters. 348. These are different sodium atom types that, depending on your simulation, can be more suitable, but I will use the standard one. 352, 355, 58, 367 to 69, 373, and 377, 79 to, and these options that are used in Charm. Yeah. So basically, we'll be using some standard options for the parameters, but you can see here that some people took the time and set the values for these atoms previously. And depending on your simulation, that could be more useful or more convenient. So let me check if I did right. Okay, so one thing is missing. I need to correct the line 42 because this is again a variable that is used by the charm program. And instead of this value, I will put append. Yeah, and now it should be fine. Okay, so here in the folder, I put previously a file called 4AKE equilibration.conf. And here you see that these are the options that are used for a molecular dynamics in NAMD. This is called a configuration file. I took it or adapted that from a tutorial from NAMD. By the way, they have very nice tutorials on how to use NAMD and VMD with the features. So you can take a look at this website. So here I put some options for the configuration file, and there are some fixed strings that we need to modify in order to run the script. So I will go through this part. And here, the first thing is that we need to fix the structure file, which is the PSF file, right? And the PSF file is called, in our case, 4AKE ion.psf. The coordinates is ion.pdb. So here we set the temperature, and the output name will be the string that will be used upon writing the output files, right? This is the first time step is 0 because we are starting the simulation. The parameters, we are using the par all 36 and the top par water ions. This is the variable we use for the temperature. The cutoff section, this will use a cutoff of 12. The switching function at 10 angstroms and the pair list distance of 14. Integration step 2, femtoseconds, rigid bonds, frequency for updating the electrostatics, temperature control. This is the thermostat part. I'm not changing anything. Periodic boundary conditions. Here we need some values for the parameters. So I put here that just if you're starting with the simulation, you can go to the file called 4ake ion.pdb. And then here at the top, you will see that there are some values for the parameters for the cell size. So in particular, the first vector will have a magnitude of 59, then 76, and 73. So, but because I ran previously this simulation, I know that these values are a bit big. So I set these values to a better value, so to speak, so that the cell doesn't start large and then compress drastically. So I will use these other values instead. And then cell vector 2. And the cell vector 3. And the cell origin. The cell origin is the value that we stored before in the statistics. Is this center of masses? So I will just cut and paste that. If you want, you can also use the value that I have here. It doesn't require to have so many digits, right? But I just copy and paste that. And actually, NumD will try to round them up. So that's it from the configuration file. In this case, we will use periodic boundary conditions with the particle mesh equal. Grid spacing is the default one. And here we are using the pressure control. The output name was fixed previously, and we put some string value. This is the frequency for writing restart files, right? And the trajectory. At the beginning, we will do some minimization step, right? And then we run the equilibration step. So also in this folder, you can find a script called numd.sh. And here you need to fix this project ID with the one that we have for the course. Which is SNIC. And the reservation. Birgitte, excuse me.
Yes.
What's the name of the reservation?
Didn't I write? Just one moment. It's. I thought I had put it there. I'm just checking. QMMM dash minus course.
Like that?
Yes.
Yeah. And in this case, if you use this reservation, then your jobs will run most probably or get started to run faster because we have reserved some nodes. Otherwise, you will enter into the queue and it will take maybe longer time to be accepted. Okay, so we are requesting for 15 minutes, but it can take less than that. And once you have these scripts ready, you can submit the job with the S batch. This is the so-called job ID. And we can take a look at the program. So it's running right now. And I can use again the job usage and copy. Copy and paste this link. And after some time, after some minutes, you will see some information if it is running. So it's running still. Yeah, so we see that we are starting to get some information from the job. So I'm concerned here about how the CPUs are used, but also you can see how much memory your jobs are using and some other metrics for the Linux system. So let me see. If I open the log file, logfile.txt, I can go to the end and check, well, it finished normally, but the point why I cannot see the information here is that it was too fast, right? It took only 37 seconds. So this is not enough to get statistic here. In the other job, it took about 10 minutes, something like that. And that's why we could see the statistics, but in this case, it was just too fast. So here you can see the information that is printed out by NAMD. And you can collect the statistics. Right. So notice here that I didn't separate the minimization part from the equilibration part. I put it in a single script. So sometimes it's more convenient and other times it's better to separate that into two different scripts. So in the case of QuickMD, it does this step for us automatically. So again, if you are curious, you can open the trajectory, although it's very short. I use the ION PSF file together with the DCD file from the trajectory. And then you can see here just a protein with some cartoon. And how it moves. It's a short, very, very tiny simulation. So if there is any questions up to this point? So I will take some minutes just to talk about the charm GUI and to show you what it can do. So if you log in into this page, you need to create an account. Then you can go to, for instance, Solution Builder. And then it will ask you about the type of protein. So in the present case, you are using 4-AKE, right? And if you type this, then it will fetch the structure from the protein data bank or the source that you choose here. And that's very convenient. It recognizes the chains and all the stuff that are present. So if we just want one chain, then you choose the chain that you want. Here you can do mutations and choose the protonation states. These are 5 bonds. If you have some phosphorylation, glycosylation, and many other options. And here you choose the type of terminal groups that you want, right? So it also has a feature in case you have additional residues and you have the parameters or you want to parameterize that, they give you some guidelines. Here you choose the type of water box. In the present cases that we watch today, we are choosing a rectangular, but maybe your protein fits better to an octahedral, and this is possible also here. The H distance is 10, and you can choose the type of atoms that you want. Right? I will remove this because I will choose the sodium chloride, recompute the solvent. So as you see, charm GUI does all these steps for you, and the process is smoother, I would say. It doesn't involve a huge amount of editing from your side as if you do that on the command line. But it also has some shortcomings. For instance, in the case you don't have the parameters or you have a special system, which is quite new. So it takes some time to set up the system, and especially in the case that your system is large. I tried once a system with 3 million particles, and it's not really possible. So here it will give you a summary of the options, and then I will choose the PME, FFT automatically, right? Is there any questions from all these topics that we have seen today? after the break, after the lunch, we will add a layer to the model, which is the quantum mechanical.
There are some questions in the Q&A document.
I see. Let me see. It's possible to do the non-cubic box on the command line. And let me see. Yes, I can come back to you on this command, how to solve the box with a non-cubic box. I will tell you some words about that later on. The next question is how to access the web page where we can see the statistics. So on the QuickMD command line, there is the so-called job usage command. Then you type the job ID that you got when you send the job with the S batch. And then here you will get a URL. Then you copy that URL and paste that on your local web browser. And then you will see the information. Let me see what other question they have. What's the best way to get the charm compatible parameters for a molecule that is not described in already existing force field, like a small molecule? Oh, well, for a small molecule here on the Maqueral website, there are some guidelines on how you can parameterize the small molecule. Most probably, you will need to go to a QMM package and then parameterize the angles, the dihedrals, the charges, the partial charges that are obtained in some specific way for charm, right? And another thing that you can do is that you can use the general force field. And in this case, you will get some initial setup for the for some parameters of the molecule, but these are only an initial guess for the parameters. Yeah. So the final results, right, can be only checked based on the simulations that you do. For instance, imagine that you get some initial parameters from the general force field, and then you run your MD simulation, and you see that the ligand is very soft in some parts and very hard in other parts. Then you need to go again and reparameterize and run into a cycle, right, of refinement. Here there are some guidelines on how to parameterize the molecule. And basically, my suggestion is that you will need to go most probably for a QMM, pure QMM method to optimize the individual terms. Yeah, as you can see here in the window that where I was running the Charm GUI, you can see that at the end, you get some options for setting the different software that you want to use for the simulations. You can choose all the software, and then the output, the scripts will be in the format of this different software. That's very convenient. Okay, I think we are 4 minutes past, so we can take now the lunch, and we are coming back at 13, yes, to continue with the second method, which is QMM.